there. Okay.
Okay.
Recording. There we go. Recording will be available too. We'll figure out how to do that. Okay, now back to my end. I think the number of books that Capers has written, and I know some of you have also written, are over 18. My favorite is The Technical and Social History of Software Engineering. I found that book fascinating if you're interested in about how software engineering evolved over the last 50, 60 years. As you know, Capers has been involved in software estimating, counting things, doing analysis, all that sort of stuff for many years. And today he's going to talk about accurate measurement and accurate estimating and excellent quality. So I want to do one thing here. I want to make this, okay. Okay, there we go.
Okay. I'll mention that I'm a fast talker, so there may not be a lot of time for questions while I'm speaking, but when it's over, you can ask questions maybe at the end or send me emails.
Yeah, just put them in chat and we'll go through the chat at the end too.
Okay. The first part is that measurement, estimation, and quality are all related. You need to know how expensive and how buggy a software project is going to be before you get started. You need to measure it while it's going along. And since bug repairs has been a major problem for software, you need to know how many bugs are going to be there. So go ahead to the next slide. The factors that influence all these things, first of all, are the personnel. You can have experienced people, you can have amateurs, then you can have processes, methodologies, ranging from waterfall through DevOps through Agile. You can have various technologies, various kinds of computer hosts, various programming languages, of which we have far too many. And then the environment, private offices, shared offices, working from home, things of that sort. All of these have an impact and all need to be considered. Next slide, please. Okay. Sizing has to be done before you really can understand cost. You need to know how big the application are. And the most common size metric, or the most effective one, is function points. You also need to know source code, how many lines of code you're going to have. But surprisingly, for big systems, you spend more money producing paper documents than you do writing code. So you also need to know the number of documents and the size of requirements and design and architecture, things of that sort. And the most expensive thing in all of software is fixing bugs. So before you get started, you need to know about how many bugs you're going to have and what are the best ways of getting rid of them, of which testing is only one. Inspections and static analysis need to be added to the set. And then the attributes that affect these things are the constraints, like do you have a fixed schedule or a fixed cost, the abilities of the team, the technology you're using, and the physical environment, whether you're working in one city in one room or whether you're working all over the world in a distributed environment with some programmers in Japan, some in China, some in America. And then the estimates, what comes out of the estimates are the staffing, how many people you need, the schedules, the effort in terms of human effort, the cost in dollars, and the quality, how many bugs are going to be delivered to clients. Next one, please. Next.
You
Can
see
we
it?
go to the next one? Apparently it's going to be a 3-slide speech tonight.
No, there's more.
No, I'm ready to go forward.
So, Dick, this is Sanjay. I think you are projecting the PowerPoint, but not the PowerPoint show. So we are not seeing the slide you might have advanced.
Oh, just a minute here. I did something. Ah. There, can you see it now?
Yeah.
Yeah.
Okay.
Okay.
You okay?
Yeah.
I tried to go full screen and it didn't work.
One other social note on Zoom technology. We have a Zoom meeting sometimes with friends who work at ITT, the ITT Corporation, and everybody has to have a martini glass and be drinking a martini while the Zoom is going on. It makes for easier conversation. Anyway, these are the commercial software estimating tools that are available for purchase, and they started in about 1973, and there may be some newer ones in 2011, but these are the major commercial software estimating tools, and they're not cheap. They're ranging the price for $4,000 or $5,000, although some like Kokomo are in the public domain. You could get them for free. Next slide, please. Okay. You can estimate a project manually, or you can use an estimating tool. And if you've got a little tiny project of, say, a few hundred lines of code or a few hundred function points, manual estimates work very well. But the bigger the system, the more hazardous and unreliable manual estimates become. And the reason for that is that you can't handle all of the calculations that need to go into a large system just from manual estimates, because there are hundreds of thousands of calculations that go into the big estimate, and you can only deal with a few dozen with manual estimates. So automated estimates are generally accurate or conservative. Manual estimates tend to become progressively optimistic, and the bigger the system, the more likely you are to underestimate. Next slide, please. Okay, this is a comparison from 50 manual estimates for projects between 1,000 and 10,000 function points. And only 4 of them came within plus or minus 5%. As you can see, as the applications got bigger, they became worse and worse and worse. So next one, please. This is the results from PriceS, Kokomo, my own estimating tools. This is 50 estimates that use automated estimating tools. 32 of them came within plus or minus 5%. Only 1 was optimistic, and the rest were slightly pessimistic. And the fail-safe mode for estimation is to be slightly conservative, never optimistic. Because if you're optimistic, that means you're going to end up spending more than you planned. If you are a little pessimistic, it means you save money, you don't spend as much as you anticipated, which is the way to go. Next one, please. Okay. First, sizing. You can count function points by hand, but it's slow and tedious. Therefore, it's better to use one of the modern automated function point sizing tools that are based on pattern matching. And pattern matching is to use a series of questions to try and compare your project with one that's already known, already finished, where the size is already known, like Windows, Microsoft Office, radar tracking systems, things where you have a lot of historical data and the sizes are known. So use checkpoint questionnaires in order to come close to that. Also, you need to know about requirements creep. If you're working on a project that's going to last 2 or 3 years, by the time you're finished, there are going to be features that you didn't think about when you got started, and they're going to show up towards the end, and they're going to make the project bigger and longer and more expensive. So you need to handle requirements creep too. Okay. You also need to know the cost of paper documents, because for large systems, you spend more money writing technical documents than you do producing code. And especially if any of you work for the government, for the Department of Defense, their documentation requirements trigger documents that are about twice the size of an IBM document or a civilian company for the same size, just because military standards tend to err on the side of too much paper. Next one, please. Okay. This is the granularity of estimates. If you're only looking at a complete project, like a compiler, you can come within plus or minus 30%, but you can't validate it because you don't know what the actual tasks were that went into that compiler. If you look at phases, like requirements and design and architecture and coding and testing, you can come within about 15%. If you look at activities, like requirements, design, coding, testing, and quality assurance, you can come within 5%. And if you come with tasks, you can come within 3%. But tasks are things like planning for requirements, writing requirements, reading, editing requirements, things of that sort. That's the sub-element of each of the major activities. Next one, please. Okay. Here's some samples. If you look at the word testing, and that's included in the project, all you know is, you know, you had it. At the project level, testing is embedded and you don't know what it is. At the phase level, testing is broken out and has its own cost bucket. At the activity level, you can show each of the kinds of testing like unit tests, function tests, regression tests, component tests, and so all of the others. And that's better than just saying testing, because you need to know how many different kinds of testing were performed. Big systems perform dozens of kinds of tests, little projects only do one or two. So you need to know that. And at the task level, you can include things like test case design, test case construction, execution, defect logging, and many other tiny things. So you can't really do this easily by hand. So this is why you need automated tools for both estimating and measurement. Next slide, please. Okay. Here are the accuracy by the size of a project. For small projects of 10 function points, which is maybe a little over 100 lines of code, you can come within 15%. And the reason that you may be wrong is that somebody might get sick during the project, or somebody might be an expert, somebody else might be a novice. So human differences and sicknesses. But as the things get bigger and bigger, the reasons for accuracy changes. And if you look at the really big systems of 10,000 and 100,000, you have to deal with requirements changes, business changes, poor quality control, requirements creep, business changes, and things of that sort. For example, I was working on a system and it was about 2/3 of the way done when the company bought another company that was in the same kind of business, and they needed to add the features of the new company to the system that was under development. So that added several months because we had to gather the requirements for a brand new company that wasn't even part of the organization when the thing started. Next one, please. Okay. Estimating accuracy by technology. If you've got good teams, good methods, good change control, high CMMI levels, you can come within 3%. If it's an average team with adequate methods, you can come within 10%. If it's a marginal project with inexperienced teams, sloppy methods, poor change control, you may become within 20%, and you won't come any better than 40% if you have novice teams, novice clients, poor methods, poor change control, and you're sloppy in everything you do. And also, you might not even finish. A lot of these projects get canceled because they drift along for so long that the CEO decides to pull the plug on it because it's obvious that they're not going to get finished. So a lot of these poor projects are finished and never go out the door. Next one, please. Okay, here are the primary reasons that project schedules stretch out. If you don't do inspections and static analysis, your testing schedule can be up to 200% longer than what you think it's going to be because you have too many bugs. So you want to do inspections and static analysis before testing begins. Also, unplanned requirements creep, which happen about 2% per month during the second half of the project, and that can add up to 20% of new features that you didn't know about when you did your first estimate. And these problems are unimportant for little projects of a few thousand lines of code or 100 function points. But if you're dealing with a really big system that may take 2 or 3 years, you're going to have a lot of creeping requirements, and there are going to be a lot of things that you didn't know about when you get started that have to be added to the system before it's over. Next one, please. Okay, here's some examples of sizes when you did your first estimate and when the project was finally released to customers. For 10 function points, it's the same when you start and when you end, because 10 function points only takes about a month. For 100, it might grow by 3%, for 1,000 by 8%, for 10,000 by 12%, and for 100,000, you might have 21% of the features that you deliver were completely invisible and unknown when you started. And 21,000 function points, that's a fifth of the total cost. That's going to add a lot of money and a lot of time for development. You can also see, if you use Agile, as most people do, the number of sprints and how they change based on the application size. Okay, next one, please. Here's a sample of different kinds of methodologies and how they lend themselves to accurate estimation. Team software process, rational unified process, Marie's structured analysis and design, Agile, all of these things are better than waterfall and cowboy, which tend to be the ones that are hardest to predict because you don't really have any control over what's going into the cowboy and waterfall projects, but you know what's going into the others, and therefore you're able to come up with better estimates for them. Next slide, please. Okay, here's some accuracy by the metrics used. if bug function points with SNAP, and by the way, SNAP stands for Software Non-Functional Assessment Process. It's things that you have to do that doesn't actually affect the size of the application, which is the main thing that drives cost. And as an example, suppose you have to change the format of a screen for some reason because a manager wanted a different look on the screen. That's not a functional thing, but it requires work to do it. So you end up with these non-functional things that have to be included, and that adds a little bit to the sloppiness, the inaccuracy of your estimates. So the best metrics are function points with SNAP. Well, SNAP is a little bit ambiguous, but it's getting better. And here's some of the others looking down the road. Use case points, unadjusted function points, agile story points, backfired function points. Backfired is converting from lines of code. For example, you can convert lines of code from COBOL, and suppose it's 110 COBOL statements per function point. That's something you can do, but it's not terribly good. Uncertified function points, logical code statements, and physical lines. Those are the ones that are least accurate for estimating whole projects. And the reason they're the least accurate is because coding is only about 30% of the total cost. And if you concentrate on that, you leave out paperwork, documentation, bug repairs, and a lot of other things. Next one, please. Okay. Here's about the number of benchmarks where measured projects that have actually been where data has been collected and studied. Function points without SNAP. SNAP is new. It's only been around a few years. So function points with SNAP, which are after 12 years, that's over 10 years, but there's more of them now. But this slide wasn't changed. Agile velocity, story points, Mark II function points, physical lines of code, NESMA and FISMA. These are some of the others. Next one, please. Okay. As a general observation, the software industry has too many metrics. It tends to use inaccurate metrics such as lines of code and cost per defect, story points, technical debt. It has sparse data on schedules above 10,000 function points, mainly because they last 3 or 4 years. And the measurement people often don't collect the whole picture. Sparse data on productivity for high systems, and sparse data on quality at every size due to leakage and poor measurement practices. How many people actually keep bugs on that they find themselves in unit tests? Almost nobody. So there are going to be gaps in your quality data because people don't measure all of the sources of bugs. Next one, please. Okay, this is the best case for estimating accuracy. This assumes experienced personnel, good methods, good quality control, good languages, and normal requirements creep. For 10 function points, you can come within 5% with automated estimates, 7% manual. 100 points, 7 and 5. 1,000 function points, 15% with manual estimates, 3% with the automated estimates. This is a sweet spot. This is where estimates are most accurate. 10,000 function points, 7% with tools, 25% with manual estimates, and big systems, 45% with manual estimates, 9%. So you can see why with a big system, you've got hundreds of people working on it. And if the people are in different cities or different countries, it makes it even harder to estimate. Next one, please. When you're looking at the schedule of a project, it's not just end to end. The activities that we carry out, they tend to overlap. For example, you start design before requirements are finished. You start coding before design is done. You start testing before coding is done. You start writing user manuals before testing is finished. And project management is there from the day it starts until it ends. So if you look at the schedule without overlap, using, say, a typical waterfall model, it might look like it's 24 months because that's the length of each of these lines. But if you factor in the overlap, the fact that you're doing several things at the same time, then the effective schedule is only 24 months. So estimating tools have to factor in the overlap in order to come up with a really accurate prediction of the net schedule of the project. Next one, please. Okay. This one deals with goals. The economic value of quality is not really well understood. Things like cost per defect and lines of code hide the value of quality. Let me show you why cost per defect penalizes quality and you can't really understand it. Suppose you've got an application of 100 function points and it's got 100 bugs in it and it took you a month to test it. Okay, so you've got 100 bugs, 100 function points, and a month worth of effort. So your cost per defect is 1 month divided by the 100 bugs. So that would be like $25 or $30. Now suppose you've got the same application 1 month, but you've only got 1 bug in it, but you spent the whole month testing it, but you only had 1 bug. So now your cost per defect has gone from a few dollars in a few hours up to a solid month because you had all the overhead of writing the test cases and running them, but you didn't have any bugs. So the more bugs you have, the lower your cost per defect. The fewer bugs you have, the higher your cost per defect. And that's why it's not a particularly good metric, because it actually works backwards. It makes the buggiest software look cheaper than the best software. As quality, lines of code also hide the value of quality. And that's because of the variations in languages, ranging from basic assembly or machine language through ultra high level languages. As quality goes up, schedules, costs, and risks come down, and methods such as Agile are good, but not sufficient. Testing is good, but not sufficient. So what you need is good methods like DevOps or Agile, combined with pre-test inspections and static analysis, plus formal testing by trained test people to achieve the best case results. Next one, please. Okay. This is, I think, one of the most important slides, because this shows in rank order how people spend money on software. And this is big software, things like operating systems and compilers, not just little toys, but things that really drive a company. Finding and fixing bugs is the #1 cost driver. We spend money fixing bugs during development than anything else. The second one is producing paper documents. And if you work for the Department of Defense, that can be the #1 cost driver, because the military standards are way too bulky. They cause the production of far more documents than are really needed. Coding is the third cost driver. And the fourth one is meetings and travel. If you're working on a big system that's being developed in Brazil, United States, Japan, and China, and you have to go back and forth to meetings, the actual cost of travel can be the #4 cost driver. Project management is the #5, and requirements creep is #6. And your estimate, in order to be accurate, you have to have all 6 of these cost drivers predicted and included in the estimate. So you need to know all 6 of these in order to have a good accurate estimate that's going to be accurate to within 5 or 10% for the overall project. Next one, please. Okay. Here are some things that help aid estimating accuracy. If you can measure your historical projects to better than 1% precision, that'll be good. You need to predict all 6 major cost drivers, plus also you need to include reuse. For many applications, you're not building the whole thing 100%. You're reusing things from older applications that you've already produced. So you need to know the percentage of code and documents and other things in a new project that are being taken unchanged and just plugged in from existing system that you already had. You also need to include requirements creep, because big systems always have that. You also need to include deferred functions. Sometimes if you've got a fixed schedule, you have to leave out functions in your first release and put them into a later release. So that will affect the schedule. You need to use the new snap size rules for non-functional requirements, things like changing the format of a screen. Adjust the estimates based on team skills, methodologies, programming languages, capability, maturity model, project type, project class, and project size, and international differences. And we'll talk about international differences too, because most of us have worked in many countries and it turned out to be a big factor. Next one, please. Okay, factors that reduce estimating accuracy. Major interruptions such as layoffs of development people, strikes, or natural disasters. Unavoidable requirements changes such as federal or state laws that impact financial applications, and you can't control that. The law is passed and you have to include it. Patent or litigation where the court orders a freeze on software and you can't develop anymore until the court case is settled. Bankruptcy of a software development company, which happened when I lived in Rhode Island. A company that was building an application went bankrupt and it shut down. And then mandated changes in tools, methods, and languages after the estimates are created. Someone may, in management, may decide that you want to use a new language that just came out, and force you to make changes after you've started and people don't know the new language, they have to learn it. Next one, please. Okay. Here are some samples of things that have negated accurate estimates. I mentioned before that at a project where we acquired a competitor in the middle of a project. This added 3 months to the schedule. Another kind, the CIO in a manufacturing company was fired and replaced by someone else. So 65% of the IT staff resigned on the same day. This delayed 25 projects for 2 months because the people weren't there to do the work. Another one, the air conditioning system in a software office building burst and destroyed a data center and offices. That caused a 2-week delay. And when Alcatel acquired the telecom business of ITT, more than 30 projects were canceled and 400 software people were laid off. So that affected all the projects that were underway at the time of the acquisition. Many of them were canceled because Alcatel already had similar applications and didn't need them. So the final one is kind of a human factor, and it's a delicate one to talk about. Sometimes accurate estimates are rejected by higher management and replaced with arbitrary and impossible schedule demands. You give an accurate estimate that this project is going to take 2 years, and your president says 2 years is too long. I want it done in 16 months. Go and do it in 16 months. So all of a sudden, you're not working with an accurate estimate. You're working with a management mandate, and you know it isn't going to happen, but the executive doesn't know it isn't going to happen, and you're stuck with it. Next one, please. Okay. It happens that because estimating tools are so sophisticated, they are often more accurate than the historical data that companies think they're collecting. And here are the major things that get left out of historical data. The most common one is unpaid overtime. Everybody probably on this thing tonight nominally works 40 hours, but most of us work 46, 48 hours a week. Like here it is. It's already, almost 8 o'clock tonight, and we're all working long after our normal hours, and we're not getting paid for it. So unpaid overtime is usually left out. Management effort is left out too, because managers aren't techies, but their costs need to be added to the project. Also, business analysts, architects, creeping requirements, technical writers, integration and database analysts, and some of the non-programming people, they perform work and they add up hours to the project, but they tend to be omitted. So if you're only looking at the cost of the coding and the work of the developers, the coding developers and the testers, you're going to leave out over half of the total effort that goes into a big project. Next slide, please. Okay, here's the way you can go about getting good information. If you do on-site interviews using a formal chart of accounts and accurate questionnaires and calibration tools, you can get historical data within 1%. You can do the same thing today using Zoom. You don't actually have to go face-to-face. In fact, because of people not being vaccinated, it's safer not to go face-to-face. But you still need a fixed questionnaire and a full chart of accounts. Self-reported data by military and defense agencies are okay, but they're not great. Outsourced contracts measured using billable hours with function points are good. Next, wait a minute. Okay, and software operations that operate as profit centers are pretty good. Next one. Okay, here are the ranges of accuracy for different types of project. Software for embedded devices, smartphones within 10%. Commercial software projects that don't track unpaid overtime but measure paid time. Small projects that have less than 3 people. Software built under fixed price contracts. Companies that don't measure seldom come within 35%. Companies that only measure DCUT, design, code, and unit tests, are leaving out over half the work. They leave out requirements, they leave out user manuals, they leave out a lot of stuff. And then finally, projects built under time and material contracts, they tend to be very inaccurate because nobody really cares. If you're being paid for all the time you work and you stretch it out to twice the length, you get paid for twice as much, so it doesn't matter. So that's why things like fixed price contracts tend to be more accurate than time and material contracts. Next one, please. Okay. These are the ones that tend to be really off the scale in terms of poor accuracy. and sloppiness. Companies that use lines of code, omit requirements, design, and other paper activities, their data doesn't come within 65%. Companies that only measure code development don't measure other work. Companies where software operates as a cost center without charges for software, where it's done for free and nobody cares what it costs. And finally, companies without formal measurement programs. So the bottom line, based on almost 27,000 projects that we've looked at over the years, 25,000 here, but it's up to 27,000, there's about 37%. The project measures capture about 37% of the effort, and 63% is not recorded. And you may wonder, how do you know that what the effort is if it isn't recorded? And you know that by interviewing the people that did the work and taking records based on the information that they give you. So you have to actually go and talk to people and ask them to explain what they did that wasn't recorded. Next one, please. Okay. These are the comparisons of accuracy. Best results for formal measurements using full chart of accounts that capture all activities, including unpaid overtime. 5% accuracy for automated estimates with best case projects by expert teams. 12% for automated cost estimates, average projects with poor quality control and change control. 15% for manual estimates of small projects under 1,000 function points, and 35% for large projects over 1,000 function points. These measures tend to be optimistic. So the better you measure things, the better you can estimate in the future. Next one, please. I have worked in 27 countries and traveled a lot over the years. And if you're working on international projects, this slide is very important because it tells you how much effort is going to go into a project. For example, assuming you're doing a project and you can do it either in India or you can do it in the Netherlands, which is going to be it quicker. Well, in India, the normal hours per month is 190, and they have 8 hours of unpaid overtime. So that's a 200-hour month. In the Netherlands, there's no unpaid overtime, and the normal work month is only 115 hours. So it's going to take a lot longer to get something done in the Netherlands than it is in India or China because of the differences in work habits of the local populations. And so you need to know this kind of information if you work for a company like IBM or Microsoft that has development labs all over the world. You need to factor in the local salaries, the local work hours, including the unpaid hours. Okay, next slide, please. Here's some comparisons of global quality 2021. I haven't been to India, but I've been to all the other countries here. I haven't been to North Korea either, nor do I especially want to. Japan has a long tradition of quality control for manufactured products and do a good job in software too. The defect potential is the probable number of bugs. That's the sum of bugs found in requirements, design, source code, user documents, and bad fixes. And a bad fix is a bug that's actually introduced in an attempt to repair an earlier bug. About 6 or 7% of bug repairs have new bugs in them in the repair itself. So in Japan, you get 4.25 bugs per function point, 96% removal efficiency. And removal efficiency is the number of bugs eliminated before you give the software to the customers. So you have a 0.17 number of bugs per function point at delivery. And if you look down the list, the United States is running about 4.5 bugs per function point, 92.5% efficiency. Germany, Russia, North Korea, more bugs and lower efficiency, mainly because things like static analysis aren't used in those countries. Okay, next one, please. This is interesting too. Since Rochester is not far from you, and it's a big place for medical devices have some of the best quality of any application, 99.5% defect removal efficiency. And there's a good reason for that, because if you've got a complex medical device like an X-ray or a CAT scan, and the software bug kills the patient, you've got enormous liabilities. So medical devices have to be very careful in quality control for the software that controls them. So that's why they're right on top. Telecom switching systems and things are also pretty good. Commercial software like operating systems, Microsoft compilers, they're fairly good. Banks and finance, fairly good, but they get sued sometimes because of mistakes. Defense, because defense builds a lot of big systems, they have a high defect potential, but they're pretty good on defect removal efficiency. Automobile manufacturing like Ford and General Motors, and then government, state, and cities, they are the worst of any, just because government is sloppy in a lot of the things they do, and software is one of them. They have 5.6 bugs per function point, only 86% removal efficiency. So there are more bugs in government software than anything else, which is why you often have errors in tax bills and other kinds of things that you get from your local governments. Next one, please. Okay, this is the activities and which ones tend to be measured completely and which one tends to be incomplete. First, requirements are usually missing or incomplete because they're done by the users, and often the user data isn't even included in your measurement. So requirements tend to be omitted. Prototyping tends to be omitted because you do the prototype before you turn on your tracking system. Architecture, same thing. Project planning, initial analysis and design. When you get down to detailed design, that's usually complete. Coding is usually complete. Code inspections are complete, and independent verification and validation is complete because it's a government mandate and they measure it. But all the other things here tend to be missing or incomplete. So what's the sense in measuring an application if you want to use the data and you've left out half of the actual work hours because there are things like requirements that you never bothered to measure? So this is a problem for the industry, that historical data turned out to be rather marginal in terms of accuracy. Next one, please. Okay, configuration control, integration, user documentation, unit testing, the work you do yourself on your own code, function testing, system testing is usually complete. Independent testing, which is primarily performed by government projects, is complete. And all the rest of the other things here on this whole page, installation and training, quality assurance, acceptance testing, all of these things tend to be incomplete. And this is one of the chronic problems for the software industry, that you can't really produce accurate estimating tools if you don't have accurate historical data, because you don't have enough facts in order to calibrate your estimating tool. So you need very accurate historical data in order to build an accurate estimating tool. Next one, please. Okay. We're up to 33 different things. And as you can see, that among my clients, historical data is only about 37% complete. 63% of the effort that goes into software projects is not recorded. And this, I think, is probably the worst precision for measurement of any manufacturing industry that I can think of. You couldn't build automobiles if you only knew 37% of the effort that went into an assembly line. And the problem with software is it's not really automated. It's almost entirely manual by skilled practitioners, and people aren't as accurate in measuring human effort as they are in measuring mechanical things. So historical data for software projects is incomplete, and that makes it very difficult to generate estimating tools. It helps if you are aware of the fact that things are incomplete and you can compensate for them. You can look at the projects that did measure these things that are missing and gain some insight on your project from the few that actually had complete results produced. Okay, next one, please. Okay, this shows the leakage. Okay. What it really shows is the comparison of apparent productivity. If you measure 100% of the work, you have no leakage, productivity is going to be 5 function points per month. If you have leakage of 25%, you measured 150 function points, 150 months, and you're going to look like 6.67 function points per month. If you only measure half the effort, you're going to look like you have 10 function points per month. And if you measure only 25%, like you measure only coding, you're going to look like you're 20 function points per month. So the productivity is going to look much better for the projects where your measurements are bad. And that's not the same as actually having high productivity. It's just a sign of carelessness and poor decisions on the part of the team and the managers. So leakage from historical data makes project productivity look higher than it really is. And it's a chronic problem for the software industry. And it's been there since the 1960s, and it's still there today in 2020. Next one, please. Okay. This shows some of the same kind of thing for leaking quality data. If you have full quality measures, including requirements bugs and measures from your clients, you can have an accuracy of 100% in finding bugs in bug report. If you don't start measuring quality until testing, only 55%. If you testing, only 45%. If you have quality measures for release, count defects, 25%. If you only count severity defects, high severity defects, severity 1s and 2, 10%. And if you don't have quality measures, no percent. So the total accuracy of quality data is only about 39%. So the software industry is embarrassingly bad in both historical data and in being able to predict the results of projects before we get started. So next one, please. Okay. Here are the origins of defects and which ones tend to be left out. Requirements defects, usually missing design. Code defects are usually tracked, but not until after unit tests. Structural defects, document defects, almost never measured. Bad fixes or new bugs in bug repairs, missing or incomplete. Defects in test cases. Test cases are complicated. You can have as many bugs in your test cases as you have in the project you're testing. And hardly anybody measures bugs in test cases. Performance defects, things where the project works, but it's slow. Usability defects, where it works, but it doesn't do what the users want. Serviceability, where it's hard to fix. And then low severity defects, missing or incomplete. And then finally, security vulnerabilities are usually not measured until they're exploited and somebody finds out about them. So it's almost never measured up front. It's not measured until after release when somebody actually hacks into your system and finds a problem. Next one, please. Okay, this is a summary of 150 major companies. If you can top 95% in defect removal efficiency and measure within 5% in both measurement and estimation, you're going to be an industry leader. And these are mostly technology companies like IBM, defense organizations like the Department of Defense, and software companies like Microsoft. Companies between 85 and 95% in defect removal efficiency. These are ordinary manufacturing companies. And companies below 85% in defect removal efficiency, actually, it's not only companies, it's state and local governments are usually below 85% in defect removal efficiency. And companies where they don't have any idea at all, their estimates can't come within 40%, and they don't really know enough to build software well. And these are manufacturing, retail, and energy companies. Tend to be by energy, I mean power plants and things of that sort. Okay, next one, please. All right, here's some smaller to medium companies. This is the same kind of stuff. Software security companies, quality companies, and tool company tend to be best. The companies that build software tools are better. Individual departments can be pretty good. Companies below 85% tend to be sloppy, and companies with unknown defect removal, no measurements, tend to be have worse than 40% errors in their estimation. And these are things like games, service group, web, and smartphone application, where people are, small teams are just building on an ad hoc basis and are careless in their measurement. And games tend to be very buggy, as you probably know if you play them. All right, next slide, please. Okay, I've worked for the government, and I've consulted with a lot of governments as well as working for actual governments. And the best government agencies, so far as I can see, and the ones I've actually seen firsthand, work in security, space, and military weapons sections, like the Navy's Surface Weapons Group, the Department of Defense. When you're building software in something like a cruise missile or a fighter, you need to be very careful in quality, or the thing won't work and fall out of the sky. So the military stuff is pretty good in quality control and measurements. The Internal Revenue Service is pretty good too, because they don't want to have errors in tax reporting. Otherwise, they could be sued for it. The kinds of government that are below 35 are state and federal departments in this group. I don't work with many with municipal departments, so I don't really know, although I suspect they're not very good. But I've worked with a lot of state governments and federal departments. And I can't say that they stand out in measurement. And finally, departments with unknown defect removal efficiency, because they don't measure, they can have 40% errors. And this includes some federal, state, and municipal departments, like right here in Sarasota. Okay, next one, please. This one was fun. The systems and embedded software folks have the best software quality and the best quality measures. Information systems for groups like banks and insurance companies have the best productivity measures and the best use of function points. Outsourced companies that make their money by building software for other companies have the best benchmarks and the best cost tracking. Commercial software has the best user satisfaction measures and the best maintenance measures. And military software has the best reliability measures and the best use of the capability maturity model for assessments and the best use of earned value measurements. So it's interesting that you tend to optimize where you make your money. And these systems and embedded software, if it doesn't work, they don't make any money. So they need good quality measures. Information systems are usually put out under pressure, so they need good productivity measure. Outsourced vendors need to be able to convince clients they know what they're doing, so they need good benchmarks and cost tracking. And commercial software needs to know sure that their clients are happy, so they have the best user satisfaction, and the military needs to know it all. Okay, next slide, please. Something seemed to happen. Like, okay, these are the industry sectors that, what year did they exceed 95% in defect removal efficiency? The format of this slide got a little messed up. Anyway, telecom software, top 95% in 1975. Computer manufacturing, 77. Aerospace manufacturing in 79. Military defense in 80. Medical devices, 83. Commercial software, 92. And no doubt there are new kinds of things like games that I don't have data on because I've never consulted or been hired by a game company to do any measures. But I doubt if they get above 95% even today in 2022. Maybe some of you have worked with game companies and have better data than I do. Okay, next one. Okay, here's some software that needs better quality control. Enterprise resource packages are buggy, hard to install, hard to customize. Data migration is different. Stock market program trading applications are buggy and have caused disruptions. Sometimes they're shutting down trading. Property assessment software is buggy. This is stuff for assessing real estate property values via software. This has led to lawsuits. And also, voting machine and vote tabulation software is buggy and easy to hack. And sometimes election results have been wrong. And as we've seen recently in the last election, there have been claims that election errors actually may have distorted the results of the election. And it's not impossible, but it's not likely. So voting machine and vote tabulation software needs to be especially careful in quality control and keeping track of all the historical data. Next one, please. Embedded applications controlling automobile engines, brakes, airbags, etc., are often buggy, and there have been hundreds of recalls and dozens of accidents. In fact, I think, didn't Tesla just recall thousands of cars because of a software bug? Software controlling electric power generation and transmission is fragile, prone to outages. I've personally lived through a couple of power shortages caused by software bugs. And so software controlling nuclear devices, nuclear generators is not always validated in countries with big nuclear plants. Who knows what kind of software North Korea has in their nuclear plants. And then finally, air traffic control has been aging, unreliable, and it's so complex that repairs or replacements are expensive and hazardous. And anybody who flies needs to be alert to the fact that air traffic control needs to be probably updated and modified. Next one, please. Okay, this is the getting down to the gist of the whole message. If you have a good measurement program, about 85% of your projects can be on time. If you don't measure, less than half of your projects will be on time. Only about 10% of your projects will be seriously late versus 40%. Cancel projects only 5% versus 15%. Defect potentials less than 3 per function point versus over 5. Defect removal efficiency higher than 95% plus total unknown. Cost estimates accurate within 5% versus 35%. Satisfaction on the part of your executive with the software performance high versus low. User satisfaction is high versus low, and your competitive abilities will be high versus low. So if you have good measurements, you tend to benefit the bottom line of your company, you benefit your clients, and you benefit the perceptions of the top management of the company. So there's every reason to go after quality control and try to be as good as you possibly can, because it benefits everything that a company does. Next one, please. Okay, I've been playing with function points ever since they came out, and we used to count function points by hand. And the problem with that, for big systems, it's too expensive and too slow. If you were to count Oracle by hand, 229,000 function points, it would take 450 days of counting, cost over $1 million. If you were to count Windows 10, 404 days, Microsoft Office, 186 days, Obamacare, 74 days. You can see that function point counting is so slow and that it would actually delay a project for a long time. So a manual estimate is way too slow and costly to be used above 10,000 function points. And that's why automated high-speed sizing is embedded in all of the commercial estimating tools. Next one, please. This shows how long it takes to size software packages using an estimating tool, such as the one we market. As you can see, it's just a matter of less than an hour, 2 to 5 minutes, no matter how big the application is, can be sized using pattern matching. And by pattern matching, I mean, you ask a series of leading questions that tries to place the new project on a matrix with projects that have good measurement data. So instead of actually counting function points by hand, you're just saying, oh, you got one of these projects? Well, these projects are 25,000 function points, so yours is going to be 25,000 too, because you're doing the same thing. So pattern matching makes function point prediction very quick, very economical, and that's why it's embedded in almost all of the commercial estimating tools. Next slide, please. Okay, this shows a bell chart that shows the overall productivity for the United States as a whole, with the midpoint of the bell being about 5 function points per month and up to 64. Next slide, please. This shows management information systems. They average about 8 function points per month. This shows system software. System software is more complicated than management information systems and has a lot more testing and quality control, so it has slower productivity. It averages about 4 function points per month. Systems and embedded software. Next one, please. Okay, military software is the least productive of anything, partly because they have rigorous quality control and partly because the Department of Defense standards cause user documents and requirements and design to be at least twice as big as a civilian project, and therefore they spend more money on paper than any other known activity. And if you ask me, is the paper valuable or useful, I have to say no. I think it's just overhead caused by bureaucracy, but it's hard to cut it down because that's just the way the military works. So military software is the least productive, mainly due to the huge volumes of paperwork. Next one. Now we're looking at the same thing for quality. Okay. The US average is somewhere between 4 and 6 bugs per function point, 75% to 90% defect removal. The best in class, which is the lower right-hand corner, have less than 3 bugs and up to over 99%. And if you have more than 8 or 9 bugs per function point and are getting rid of less than 65%, that should be considered to be professional malpractice. Next one, please. Okay, this shows the same chart, only it shows it by size. And you can see that 100,000 function points has many defects per function point and fairly low defect removal efficiency. As the applications become smaller, you have fewer defects per function point and higher defect removal efficiency. Next one, please. It's not the way it should be, but it's the way it is. And then this is the quality based on different methodologies. Cowboy, waterfall, capability maturity model 1, iterative, pair programming, agile, CMMI 3, extreme programming, CMMI 5, TSP and RUP, Integranova, and TVAC. You can see that the older methodologies don't give you very good quality, but the new ones such as agile and TSP and RUP move you down towards the best in class corner of the chart. Next one, please. Okay, this is different kinds of defect removal efficiency. If you only use manual proofs or test by developers, you're not going to be very good. Test by certified testers are a little better. Test plus static analysis, test inspections and static analysis, and then automated proof and requirements models bring you down up here to the very bottom, up to 99% defect removal efficiency. And you can't really go above 99% in most cases. Okay, next one. Okay, here are some actual samples of the kinds of projects that fit on the same slide. As you can see, bundled outsourced contracts are the worst. Stock trading software is not very good. Local taxes and property assessment, billing and retail, ERP, energy, manufacturing, open source. And then finally, towards the bottom are embedded software, telecom, medical, avionics, and weapon systems. They tend to have the smallest number of bugs per function point and the highest defect removal efficiency. Next one, please. This shows the results by country with Russia, China, the US, European Union, United Kingdom, and then Malaysia, Brazil, Mexico, South Korea, India, and Japan, with Japan being probably, or they were slightly better last time I was there, probably still better today. India's pretty good too. Okay, next one. Oh, this is the nearing the end. Finally, software estimating is important and complicated. Parametric estimates are better than manual. Function points make estimating easier. High-speed function points allow you to estimate early and quick. Lines of code metrics are hazardous and dangerous. Cost per defect is hazardous and dangerous. Story points and use space are inaccurate and hazardous. Technical debt is interesting, but hasn't been really validated. Good estimates and good measures lead to successful projects. Bad estimates and bad measures can lead to disasters, cancel projects, and litigation, and eventually lead to people being fired for non-performance. Okay, next one, please. All right. The accuracy of a software estimate cannot be known unless the accuracy of historical data used for comparison is also known. You can have an estimate that's accurate to within 1/10 of 1%, but if your historical data is only accurate to within 50%, how are you going to know? You need to have proven historical data in order to understand the accuracy of your estimates. And one of the best ways of calibrating an estimating tool is to use it on projects that have already finished rather than new projects, and see how close it comes to projects that you've already finished where you know you have actual estimates. Okay. Okay. The last slide. Competence is predictable. Incompetence has random results. So the better you are, the better things are going to be and the better prediction. And unfortunately, the software industry doesn't have a great reputation for competence. We have been accused, sometimes justifiably, for having too many cost and schedule overruns, too many bugs in the software when it's delivered. But I believe that's the end of it. Okay, thank you. See what comes up. Summary and conclusion. Okay, good measurements lead to accurate estimation. Accurate estimation leads to high quality. High quality leads to control projects. Control projects can come within 3% of the estimate. And uncontrolled projects are hazardous and experience schedule delays, cost overruns, optimistic estimates, negative return on investment, cancellation, poor quality, and unhappy clients. And I could mention litigation, but I ran out of space on the chart. So I do expert witness work in a lot of lawsuits for software that was canceled or had too many bugs in it. And that's not a pleasant experience. Okay, next one. Okay, these are just the references.
I also put in here all your clients that you sent me, just so where all this data comes from. It's in my opinion, very impressive.
These are the companies I worked with over the years to get the data that I use tonight.
Yeah. So thank you very much, Capers. Let's see what the chat has to say, huh?
Okay.
Let's see. Maybe I can work this from top to bottom. Let's see how that goes. There we go. Oh, Code Freeze. Code Freeze is next week. It's a program put on by the University of Minnesota Software Engineering Center.
I'm sorry, I couldn't understand what you said. Can you say it again?
Code Freeze is a conference put on by the University of Minnesota Software Engineering program, usually in the second week of January, and that's where the title Code Freeze comes. If you're interested in attending, there's usually about 150 folks that show up, and this week yours going to be on Zoom. Let me know, and I'll make sure you can get an invite.
Okay. It's just let me know the dates and the time and everything. I mentioned we have relatives coming in.
Reminding me of these things.
Yep.
John, the name of the book that I mentioned was The Technical and Social History of Software Engineering. If you Google Capers and books is published, it's right on the list. I found it fascinating as a reminder of what's going on in the past and what it leads up to. Let's hear what else here. Tom. Oh, success. There's a book on from Tom, I believe that says.
Yep.
Tom Gill, Success.
Yeah, Tom writes a lot of books too.
Yeah, yeah. So if you Google Tom Gill, I'm sure you'll find interesting reading material on software engineering value and all those kinds of interesting topics.
Thank you.
Alex,
I like to give it away.
Oh, Alex looked up the book I mentioned. Here it is. I bet. Well, I don't think I'll go there. I might not get back. But it's on the list, and you'll find it easily. Let's see. Thank you, Alex. It makes you feel better. I got a scotch. You can see how technical these guys get. An old-fashioned here. Jesse says, we can see your messages recording. I screwed this up. Sanjay, he's telling me the reason is not showing up because you didn't have select the new windows here. I screwed that up. I'll learn next time. Michael John, how are estimates derived when there is a research component? There is a real question. How are estimates derived when there is a research component?
What's the meaning of the word resource in this context? Is it human effort, or is it the mix of the technical staff? How many different specialists are there? I'm not sure what the word research means.
And I think in Michael's case, he's wondering about where there's really fundamental research going on, figuring out how to what could be done. I think, and if Michael's here, he can expand upon that a little bit.
Can you hear me, Dick?
Mm-hmm.
Hello?
Yes. So my question is, you know, you have a project, large, small, I guess doesn't matter. And there's some aspect of it, some part of it where you really don't know how you're going to do it. You're going to have to do some research to try to figure out some
You said
aspect
research.
of it.
I thought you said resource. Okay, research. Okay, that's a very good question, a very solid one. Normally, let me step back. Probably 80% of the software in the world has been built hundreds of times before, and you don't need to do any research. If you're doing something that you've never done before, some new software for a spaceship, or for some kind of a defense application, or some new kind of business where you do have to do research, that unfortunately is outside the data that I've collected. And although I've been part of a few of those things, I don't have any real solid data on what would be the total impact of research on novel things that you've never done before. But it's a very solid question.
Okay, well, thank you.
Next question.
This is Elizabeth. Can I comment on that?
Sure.
I would break it into two separate projects, if not more sub projects. So you do the research first, because if you can't succeed at the research part, there's no point in building the rest of it.
Okay, anybody else? We'll go to the next one. How does estimation work with Agile projects?
With agile projects,
Yeah, which embrace change, even requirements changing. Would the estimates be done per sprint, for example? So this is Robert.
the estimating tools can estimate individual sprints and then the aggregate of all the sprints. Most commercial estimating tools have an agile mode that seems to work very well.
I'm going back a minute. Oh, okay.
They predict the number of sprints, they predict the effort of the sprints, and some of them even predict the kinds of people that should be in the sprints.
Oh, wait a minute.
Yeah, this is Robert.
Yeah, I gotta go.
But the part of the question I was asking related to Agile was, if the Agile project decides on requirements changes in the middle because of customer or user feedback, you'd have to re-estimate the next sprint based on the requirements change, I was thinking. So that's why I was asking, would the estimates be done sprint by sprint, or would you try to do the entire project? Because you may not know what the requirements are up front.
Well, if you don't know the requirements or even part of them, you can't really do an estimate because the end goal is invisible. So you need to have either pattern matching, say that this project is going to look like a project that we do know about, or if it's just open-ended, you don't know what you're going to do and you don't know if any other projects have ever been done that are the same, then you can't really do an estimate because you're jumping off into the unknown, into space. But how many projects are like that? In 50 years in software, I've mostly seen projects that were similar to things that have been done many times before. I've only seen a very few that were novel being done for the first time.
Well, here's the same thought on any thoughts used to test-driven development in addition to inspection and static analysis before testing starts.
I'm sorry, I didn't quite hear.
Is there any thought about using test-driven development prior to testing starting?
Yes, test-driven development is a standard feature you can turn on in estimating tools.
Okay, Pat.
You can dial in the kind of technologies you plan to use in most of the commercial estimating tools, and test-driven development is one of them.
So here's Pat O'Toole. Since some of the underlying causes of estimating inaccuracy are known based on historical data, can't the project add X%?
So,
Yes.
Capers, where I'm going with this is I do a lot of appraisals in China. And in some organizations, what you find is on average, the projects are coming in 5% over their estimates. So
Yes.
one of the things I would tend to recommend is just, if we think of that, a normal curve is kind of the output coming from estimates, we're going to be somewhere within a range. Just readjust it. After you come up with your estimate the best way you can, just add 5% to shift the normal curve to what is the real center of gravity, right? The plus 5%,
Yep.
and use that as a more accurate estimate. Does that
Well, you
make
can
sense?
put in a contingency factor in some of the estimating tools that has
Right.
that effect.
Okay, okay.
So better known as management contingency. Tom. Oh, here's an estimation or control paper SQP. Again, that's up on Tom Gilb's website. Robert. Another industry area needing better quality control is cloud computing. Witness the multiple problems that Amazon AWS has experienced recently, causing multiple organizations using cloud computing to go down or suffer outages or data loss.
Cloud computing is one of the newer kinds, and it's one that has insufficient data from completed projects, historical projects. So there's sort of a semi-gap in the estimating technology because not enough cloud projects have been included. But it is a troublesome area.
Does anybody really know what the quality of AWS is in terms of typical software measurements?
Well, it's got to be measured. I mean, it's got to be expressed in things like defect potentials and defect removal efficiency, because they work for anything.
Yeah. Okay, the next one from Tom again.
They actually, AWS is doing static analysis on their software. They're not, I mean, obviously they're not going to give the results to the public, but they are looking into it. At least the structural aspects.
Yeah, I would imagine that'd be true. Next one, Tom. This is from as familiar as I am with Caspers' writings. This talk has lots of interesting insights, and we know they are based on data, not bare opinions, as so many do in our trade. Go Caspers.
Thank you. Thank you very much.
Bill Curtis, there is now an ISO standard on automated counting for base function points. ISO standard 19515. Several automated tools actually produce an actual function point count based on full software analysis.
That's true. And my greetings to Bill. He's an old friend.
Yeah, Caspers and I worked together 40 years ago.
Yeah.
Yeah, in fact, Caspers was one of the motivations for, and one of his former colleagues, David Heron, led the development of that standard to kind of finally get something out there to solve the inconsistency and cost problems with manual function point counting.
Is it widely used?
There are some of the major static analysis vendors have picked it up and have implemented it. So, and there are some major companies that now have moved to that because the consistency and cost issues are so much better. The first time you use it, expensive because you've got to load in your software and set it up for analysis. But after that, it's fast.
Okay.
And that's the case with all static analysis. Is the first time, if you're doing a system level analysis, it takes a while to get everything loaded in, make sure you've got all the transactions identified and what have you. But once that's in the system, then from then on, it's pretty much updated based on changes, and then it runs very quickly.
Thank you. This is a good input.
Thank you, Bill.
Yeah.
Good to talk with you again, Bill.
Yeah.
Tom again, dynamic design to cost copes with imposed deadlines and fixed prices. Another talk from Tom on his, looks like it's on his website. And then we got thank yous. Thank you, Capers. Highly helpful and informative sessions. The next point is this PowerPoint available to share with colleagues? We will store this on the TwinSPIN website, the PowerPoint, and it's available to anybody. And we'll send the link out to everybody where you'll find that stuff. It's actually in the meeting announcement. If you go to that website, you'll find it. And we'll store this, the PowerPoint will be up there, along with, I'm going to try to figure out how to put the meeting recording up there so anybody wants to see it. Alex Dietz, my company is starting a fresh software medical device project with no history on which to base estimates. It's a small team, 5 engineers. What can I take away from this presentation to help this team put together a good project estimate?
Well, you should look at commercial estimating tools, of which, since I sell them, I don't want to be pushing mine, but look at any of the commercial estimating tools and make a selection. You can ask some of the other people here for their ideas, and that you have to be sure, if it's a medical device, that your quality control is state of the art, because you don't want to kill patients. So be sure you use static analysis inspections, testing by testing specialists, test-driven development. You need to be very careful with quality control for medical devices.
A possibility is, I don't know how you feel about it, Capers, but a possibility, Alex, is SLIM from, we had that presentation here early in the year.
Did you say SLIM?
SLIM, S-L-I-M.
Yeah.
Because it's got a big database behind it as well that may help you get started.
Yeah. Well, you need data behind your estimating tools, and the more data you have, the better it is.
Scott Myers, do you have any data on how to use formalized requirements in a model, in how they impact software estimates?
I have data on the contribution of bad requirements to poor quality. I have data on the number of pages of requirements per function point. And I have data on ways of trying to remove errors from requirements before you get started. Mostly inspections work better on requirements than anything else.
Scott, you want to say something more what a formalized requirement is?
Just my company and many others are getting big into model-based development. So just curious how model-based development really impacts the whole software estimating process, the defect removal rates and all of those other quality measures.
Yeah, it does. But the commercial estimating tools handle model-based development.
That's it. Anybody else have any questions or discussions?
Hey, just a quick question. Capers, are there any emerging estimation technologies that you've seen? I mean, this was kind of a depressing talk, right? You were essentially telling us how bad we are and how bad we've been for the past 40 or 50 years at doing this estimation thing. Are there any emerging technologies that you've seen, artificial intelligence, anything like that, that gives you hope that we're going to get better over time?
I think artificial intelligence is going to make some positive improvements in software quality control and software estimation. And but it takes a big company who's actually with firsthand experience in artificial intelligence to do the work, to do it. So it has to be somebody like a IBM or a Microsoft that's actively involved in artificial intelligence to have access to the knowledge.
Anything other than artificial intelligence that you see on the horizon that could be useful?
Well,